u of x naught plus h minus f of u of x naught divided by h, that is equal to f prime, approximately equal to anyway, f prime of u of x naught times u prime of x naught. All right? So in the limit h goes to 0, the difference quotient of the composite function, the derivative, is exactly equal to this. But that's the chain rule. It says the derivative of the outside function evaluated at the inside function times the derivative of the inside function. And if you really want to get right down to it, it really is just this pre-calculus example. Like, have you guys ever done this? Suppose you've got like f1 of x equals to 3x minus 7. Let's say f2 of x equals to 11x plus 2. What's the composite of f1 with f2? We do what? f1 of f2, so f1 of 11x plus 2. And then we plug 11x plus 2 into the formula for f1. So we get 3 times 11x plus 2, right? Minus 7, which gives me 33x minus 1. My question to you is simply this: how is the slope of the composite related to the lines which are composed? Can you see it? The slope of f1 was 3. The slope of f2 was 11. f1 composed with f2 has slope 3 times 11. This is not an accident. This is what the chain rule is all about. When you compose two functions, the tangent line of their composition has a slope which is simply the product of the slopes of the tangent lines which are composed. That's all the chain rule is saying. It's really just example 15 done locally. And this is this sketchy proof. I have a more careful proof using that Car Theodori business in the notes if you want to look at it. All right, so it's a good amount of calculus for one day. I do want to look at the, let me just get the projector out and just look at it with you guys before I forget. I don't want to write it on the board, but it's good for us to like look at it together for just a minute. If I can find it. Well, oh man. I will eventually find my notes. I think I hid them on the course website, didn't I? There they are. Kind of silly to download them when they're on my computer, but whatever. All right, so let me get this out here. So here's the first proof in my notes is essentially the same as the thing I just did on the board. It's just done a little bit more carefully, and that is to look at the difference quotient for the composite and to replace the inside function and the outside function with their tangent line approximations as a means of calculating the limit. All right. So it's mostly correct, but yeah, we'll get back to you. Shush. The proof at the end of this section over here, I would say is slightly more rigorous if you're interested in that sort of thing. So here, I've got two functions which are composable, and the I and the j are just intervals which make sure that the image of the function of f sits inside the set where the outside function is differentiable. And then what I do is I apply Carr-Theodore's theorem twice. Once for the outside function, well, inside function here, I guess, f of x, and then the g of the outside function g, I also apply Carr-Theodore's theorem like that. And then I argue that the composite, I think, of their Carr-Theodore functions serves as a Carr-Theodore function or something like that. Anyway, I'm able to calculate the difference quotient of the composite explicitly using those Carr-Theodore functions like so, and just using basically the composite limit law. This is a completely rigorous proof of the chain rule if you care about this kind of thing. And if you don't, it's okay, but if you're a math major, you should start caring at some point, all right? There may be no math majors here. I forget to check. Is anybody a math major? Aha, there exists one. And Emma's also one. If you move the pen on your hair like that, that means you're a math major. Don't have to be so definite about it. It's still early. You could change. Okay. I feel like I'm just being pandered to, but I'll allow it. Let's see here. We've turned the light back on. So one of the things you guys had trouble with on the test was what? Actually, that's a question. Would you guys rather me just go over the test in the last minutes rather than algebra review? It's your class. Algebra review or test overview? You guys have no preferences whatsoever. I would definitely not play poker with you guys. As I always say, though, it's because I don't know the rules. So that's mostly what keeps me from it. I'll put this away then. So let us talk about another algebra problem that I saw a lot of people still not able to come terms with is factoring a quadratic. Unless the quadratic happens to be something nice and bookish, you're stuck, right? What if it's ugly? What do? There's no need to be stuck. So factoring via completing the square. This is a tool which will factor anything. So like algebra example 1, suppose we're up against x squared plus 10x plus 2. All right? This does not factor nicely, I promise. So let us complete the square. What we do is simply this. Take half of 10, which is 5, and you square it. By doing that, I have now added 25. So I must subtract 25. That plus 2 is still there. So what do we got? We have x plus 5 squared minus 23. And then, standard trick, this factors as follows. X plus 5 plus the square root of 23. X plus 5 minus the square root of 23. All there is to it. Algebra example 2. What if there's a pesky 2 out front? That's pretty hideous. 2x squared plus 3x plus 7. Can we factor it? I have no idea. I mean, actually, I do have an idea. Yes, always, always yes. We can factor any quadratic. There is no quadratic that you cannot factor if you allow yourself complex numbers. If you don't allow yourself complex numbers, you still need to be able to definitively show yourself that it cannot be factored with real numbers. Factor the 2 out. We've got x squared plus 3 halves x minus 7 halves. Now that I have it in this format, I go back to the completing the square thing. I take half of the coefficient of x. What's half of the coefficient of x? What's half of 3/2? It is 3/4. I square that. I have to subtract 3/4 squared. And I've still got my minus 7/2 from before. All right. So what you got? You got the 2 out front. You've got x plus 3/4 squared. And that's a 9/4 minus a, that's minus 9/4 and minus 14/4, which is, what? What's 9 and 9 plus 14? Whoa. That's an accident, guys. That's messed up. 23 over 4. Minus 23 over 4. Whoa, that is... Whoa. You understand, I just made this up, right? I just made this up. That happened. Look at that. Come on. God has a perverse sense of humor sometimes. Let's hear 3/4 minus the square root of 23 over 2 times x plus 3/4 plus the square root of 23 over 2. Factored. Just like that. Every quadratic you can factor using completing the square. My last example for today, algebra example 3. Suppose you've got x squared plus 6x plus 100. Does it factor? All right, so that x plus 3, quantity squared. Take half of 6 is 3. That means I have to subtract 3 squared, which is 9. What's 100 minus 9? 91. So I got minus 9 plus 100. Lo and behold, we've got x plus 3 squared plus 91. At this point, you say, aha, prime. That's as far as we can go. It cannot be factored over the reals. If you understand carefully these 3 examples, you don't need to ever not be able to factor a quadratic again. You guys, I had x squared plus 8x plus 1. I get an example in class. It was in your homework. I had like 3 different places in here, and there's still, and it was on the test, and still many of you are not doing it. Like, I don't know. Like, I need, I don't know. I need to get through to you. You need to learn this, okay? Or be really competent in the other way of doing things if you don't like my completed and square way. So, anyway, that's it.